All right, so ladies and gentlemen, we're going to do the middle section of this kinetics chapter. And if you would, your equation sheet on the front side, you'll notice that there is a small section at the bottom that says kinetics. There's not a whole lot there, but just have your equation sheet out, so you can reference it when we need to. So let's just review for a little bit. Okay, we're in this chapter of kinetics. It's all about speeds and rates of reactions. Okay, and the primary thing that we focused on last class was how do we write what's called a rate law. And if you remember, if you look back at your notes, what did those look like? Rate equals lowercase k, concentrations raised to some power, and our job was to use a chart of data to figure out what those exponents were. Okay? And let's just make sure we are clear, because I think I made you write this down in your notes, and maybe you did, maybe you didn't. But when you see the word order, where should your brain go? The exponent, okay? So if I say that a certain set of data is first order data, or this reaction runs under first order kinetics, all I'm really saying is that the rate law has an exponent of 1. That's really all I am saying, okay? So here is a rate law with some reactant, and it's raised to the first power. If this thing in the middle is kind of bothering you, let me just remind you of what it is, and it's not something to be afraid of, okay? This is just showing how a rate for any reaction, doesn't matter what order it is calculated, okay? Rates are always calculated by a change in the concentration of, in this case, a reactant, divided by a change in time. If that's bothering you, then ignore it. Focus here. Here is that rate law that we determined last class, okay? And it had a name. This type of rate law we called a differentiated rate law, or a differential rate law, okay? There is another type, okay? And those of you that are calculus-minded, you're going to see some more calculus connections today. This is a differentiated rate law. Here's the other type. It's called an integrated rate law, and it looks like this. For first order data, this is what the integrated rate law looks like. And here's the good news. You don't have to memorize it. It's on your equation sheet. What I would like for you guys to do, look at how it is written on your equation sheet. Okay, so look down at your equation sheet and then look up at how it's written here. Down, look up, down. What did I do? Yeah, I just moved the ln, I just rearranged it a little bit. And there's a reason why I did that. And I so wish the College Board would, instead of writing the integrated rate law like this, I wish they would write it like in this arrangement, and you'll see why. Okay? Now, again, I will explain why I have this rearranged, but let's just get our bearings here. What's ln? What is that? Natural log. Okay? Now, don't let that freak you out. I'm not a big fan of dealing with logarithms, but in this class, ladies and gentlemen, the extent of your knowledge of natural logs is, can you push the button on your calculator? Yes, you can. Okay? What do brackets mean? Molarity, okay? This lowercase k is the rate constant. It's the same k that we dealt with last class. T is time, ladies and gentlemen. This is representing time. And that's going to open some opportunities for us because the rate laws that we wrote last class, you'll notice, ignore what's in the middle. A differentiated rate law does not have time as one of its variables. An integrated rate law does. Okay, here's natural log again, molarity. What is this little sub-zero? Initial. The molarity of this reactant at time 0. If this is the initial molarity, what do you think this is? Final. And let's be more specific. This is the molarity after some time has gone by. Remember those graphs from last class. From the beginning of a reaction to the end, what happens to the amount of a reactant? Does it decrease or increase? It decreases. So this number, whatever it is, should be bigger than that one. Okay, because reactants decrease over time. Now let me explain to you why I prefer to write out the integrated rate laws in this arrangement. Because it makes it easier to see this connection. This is your general formula for a line, okay? Linear data. And let's just piece things together. In place of y, I have the natural log of a concentration. In place of, what's m represent? Slope. Negative k. X is time. What does b represent? Y-intercept. The y-intercept is the natural log of the initial molarity. Okay? Now, don't write this down yet. Okay? Just listen for a moment. Here is the situation you are going to be presented with. You will be presented with some data that will have this in it. Time and molarities. Okay, a chart of data. Now, let's make sure that we recognize how a chart of data like this is different from what we saw last class. Look at your notes from last class. We had tables of data. We did multiple problems. We had molarities in those charts, but what was in the column on the far right-hand side? Rates, initial rates, speeds. That is not what we have here. Here, we have times and molarities. And this is what a question is going to ask you. Given data like this, is this data first order data? Yes or no? Prove your answer. Okay? How you might prove it is by graphing it. Okay? Now, what are you going to graph? Well, you're going to put time on the x, but notice it's not just molarity on the y. It's not just concentration. It's the natural log. Do you all agree that that line is perfectly straight? Do you agree? Okay. If, and that's a big if you plot data just like this and it comes out to be linear, straight, then you can say, yes, this data is first order. We will talk about what does it mean if it isn't straight, and what do you do in that case? We'll get there. Okay? But I want to highlight something for you here. Please don't memorize what is on this graph. You don't have to. What's on the x-axis? Well, what's in place of x? Time. What's on the y-axis? Don't memorize it. What's in place of y? The natural log of the concentration. Okay? And this equation is on your equation sheet. There's nothing to memorize here. So the point is, you have some data. If you graph time on the x, natural log of concentration on the y, and it comes out to be straight, then you can say, yes, this data is first order. If they asked you to write the rate law, you could then go and say, okay, I can do that now. Rate equals. And since you are now confident that it's to the first power, you could write that rate law. Okay. And again, we'll talk about what happens if it doesn't come out to be straight. What do you do then? And what does that mean? Okay. Now, what else could you be asked about? You could be asked about a half-life. You could be asked to solve for it. Let's make sure we remember that definition. Guys, a half-life is a length of time. It's a time. Could be in seconds, minutes, fortnights. Do you know how long a fortnight is, just out of curiosity? 2 weeks. Okay. Everyone should know that. That's good general knowledge for life. Okay. A half-life is the time it takes for a reactant to decrease its original concentration by half. I mean, I'll just use a mass, for example. If I had 100 grams of reactant at the beginning, how long would it take for that reactant to be consumed so that it's down to 50 grams? For some reactions, that's a nanosecond. For others, that could be 10,000 years. Okay. There's an equation. Don't memorize it. It's on your equation sheet. It's there. Okay. This is the half-life. This is your rate constant. Okay. So if you are asked to solve for something, for a half-life of a reaction, and you know that it is first order, you are permitted to use this equation. If it's not first order, then you can't use this equation, and we'll talk about that. Something that I just want to call your attention to here. Do you all see molarity or concentration anywhere in this equation? Yeah, me neither. The half-life of first order reactions does not depend on concentration. And that might seem a little strange, you know? Doesn't the half-life depend on how much you have? No, it doesn't. If it's a first order reaction, it does not. Okay. Just want to call your attention to that. So let's look at a sample problem. And this is really very, very easy. Okay. It says, a certain first order reaction. Stop right there. Don't read any further. They are telling you it's first order. You didn't have to figure that out. Might I suggest, once you know, if they tell you what kind of order it is, in my mind, I make a list. Okay, what are my available equations that I could use? Well, if I know it's first order, maybe I'm using this. Maybe I'm using my differentiated rate law. Maybe I'm using the integrated rate law. I I also have a half-life equation available to me. Maybe I'll be using that. Okay, I'm just writing out what my options will be. So let's keep reading. It says, this reaction has a half-life of 35 minutes. Well, chances are I'm probably going to be using this guy since they said half-life. Calculate the rate constant for this reaction. Which variable is the rate constant? Okay. This is really easy, guys. Plug in and solve. Let's do it. Okay. Does K have units? Yes. And what's annoying about it? It depends on the problem. Now this one's actually easier than what we were dealing with last class. Just look right here. This number is in units of minutes. This has no units at all. So what must the units of K be here? 1 over minute, an inverse minute. I'm going to write it like this, minute to the negative 1. Okay. Part A, solved. That was easy. Let's look at part B. Part B says how much time. Stop right there. Time is what we're solving for. Is time a variable in here? This one? No. So I'm probably not using that one. We've got time here. We also have time in this one, but this is a very specific time. That's a half-life. Let's look up here. How much time? I'm going to circle it. That's my unknown. How much time is required for this reaction to be 65% complete? All right, well, this is my unknown. Do I have a number to plug in for K? Yeah, we just solved for it. What about here and here? We've had a semi-similar situation with this. If you're dealing with a percentage, what might be a nice, easy number to plug in as my initial? How about 100? Okay. If I start with 100%, now don't start plugging in numbers immediately. Be careful. This molarity represents what concentration remains, is left over. If you start out with 100% and this reaction is 65% complete, how much do you have left? 35. 35 is what should go there. So let's do it. Let's plug everything in. $52. Yeah. 52 what? It's a time, right? Yeah. 52 minutes. How did we know it was minutes? Because all of the other units were in minutes or inverse minutes, something like that. Okay. Problem solved. But the point is, I was only able to use this equation and this equation because I knew it was first order. So what if it isn't? What if it's second order data? Now you're going to get sick of me asking you this. You hear the word order, what do you think? Exponent. Second order. All that means is its rate law now has an exponent of 2. That's all that means. Second order data has its own integrated rate law. It's not the same one. It looks like this. Don't memorize it. It's on your equation sheet. Now let's do this again. Here it is. Look at how it's written on your equation sheet. Look down, look up, look down, look up. Do you see what I did again? I just rearranged it. Why do you think I rearranged it? So it'll look like y equals mx plus b. Yeah, exactly. Same reason. Okay. So I want you to look at this carefully. All right, let's talk about what's going on with both of these graphs. Okay. Come back to what the original question will present you with. Time and molarity. Let's say the question now says, is this data first or second order? Which one is it? Prove it. So you say to yourself, okay, let me test to see if it's first order data. Let me try that out first. So think about what we just talked about. We put time on the x, natural log of molarity on the y. Does this look straight to you guys? No. So what does that say to you? That this graph was not linear. It's not first order. So you say, okay, let me see if it is now second order data. So you try a slightly different plot. Please don't memorize what's on these axes. What's on the x-axis? What is in the position of x? Time. What's on the y-axis? Not natural log this time. The inverse, 1 over molarity. Does this look straight to you? Yeah. So we say, yes, it's second order. Okay. So if that plot, different from what we were looking at last time, if this particular plot gives you linear data, then you say, yeah, it's second order. And if they said write out the rate law, then you could confidently write rate equals K times your reactant to the second power now. Do you think I could ask you about half-life for a second order reaction? Yeah. Okay. Now, here's the thing, and I'm going to get on my soapbox a little bit here. This annoys me. Look at your equation sheet. Are there any more equations on here that we haven't looked at yet? No. That's all you get. The equation for second order half-life is not on here. And what annoys me is when teachers will say, oh yeah, sorry guys, you know, that half-life second order equation's on there. I guess you're just going to have to memorize it. No, you're not. No, 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 you're not. Okay, let me show you. A half-life is a time, right? Nod your heads. It's a time. Okay, well, let's say you are supposed to solve for the half-life. Well, you have to be given or have found somehow that rate constant. What if, just what if you did this? For this initial molarity, what if you put in the number 100 and over here you put 50? Hasn't this number been cut in half? Nod your heads. Guess what? If you solve for that t, you have solved for the half-life. You don't need an equation. You already have it. If you don't like the number 100, give me a number. Any number you want. 2. Fine. Put the number 2 in there. What are you going to put there? 1. Give me another number. 200. Fine. 200. 100. Any number you want. Put it there. Cut it in half. You will be solving for the half-life. It drives me nuts when teachers tell AP students, oh, you're just going to have to memorize that equation. No, you're not. Okay? Now, if you want to see what the equation is, here's what it looks like. Okay? for second order data, that is how you solve for the half-life. You don't even need to write that down if you don't want to. You don't need it. You have it right here. Okay? But I do want to call your attention to the fact that unlike first order half-life, which you are given, although you honestly don't even need to be given this one, but whatever, they gave it to you. This one doesn't have molarity in it. This one does. That's just something I want to point out to you. It's a little bit of a difference. All right? So what if it's not first order? It might be second. What if it's not second order? What else could it be? It could be zero order. And I know what you're thinking. Those of you that are, a little OCD like I am, why would she go in that order? Why would she go 1, 2, 0? Ugh. I know. It annoys me a little bit too. The reason I present this one last is because this one just doesn't come up that often, right? Most of the time, you will not be dealing with data that is zero order, which is why I put it last. Okay? But for the third and final time, guys, you see the word order, what do you think? You got it. What is anything raised to the 0 power? 1. How could I write this differentiated rate law a little simpler? Rate equals K. That's it. Remember what we said. K has different units for every problem, but the units for rate do not change. Do you remember from last class? What are the units for rates always? Molarity per time, some unit of time, okay? Or some unit of concentration per time. Well, if rate equals K, that means K will have the exact same units. Okay? Just wanted to point that out. Does zero order have an integrated rate law? Yes, it does, and it looks like this. Now, that is not on your equation sheet, but are you ready? Not to panic. Look at the integrated rate law for first order right here, the very first one you're given. Just cover up the LNs. Take them away. If you just take away those natural logs, voila, you have the integrated rate law for zero order. Okay? I hate to say memorize that, but you can remember that, right? Right? Yeah, you can. Now you guys tell me, looking at it like this, if I wanted to graph to see if something is zero order, what would be on my x-axis? Time. What would be on the y-axis? Just plain old molarity. Okay? And if it came out to be a straight line, then you would say, yes, my data is zero order. Do you need to memorize an equation for the half-life? Tell me no. No! You can use this. Pick an easy number to work with, like 100. Put in 50. You could solve for the half-life. Okay? Let me bring everything all together. Okay? This chart, which summarizes everything that I have said today. I'm sorry to say, this does not come out of your textbook. This comes out of our old textbook. Our new textbook that you guys have, unfortunately, doesn't have something like this, but I'm giving it to you. This chart is your new best friend for the next 2 weeks. Say hello.
Hello.
Hi. Hi, friend. Okay. And again, this is a place where, like, some things that other teachers may say, it really annoys me. Like, oh yeah, you just got to know this chart, guys. You just got to memorize it. No, you don't. No, you don't. Okay? Let me show you how you don't have to memorize really anything here. What does order mean again? Are you sick of me asking? Exponent. You don't need to memorize these differentiated rate laws. All you're changing is the exponent. The integrated rate laws, these two are given to you on your equation sheet. What's an easy way to remember this one? Just cover up the ln's, and there it is. Plot needed to give a straight line. Don't memorize it, guys. What's on the x-axis? Time. What's on the y? X, Y, X, Y. Relationship, and this is important because this you might be asked to solve for sometimes. Relationship of rate constant to the slope of that straight line. Don't memorize it. It's there. What's in that position of m? Negative k, positive k. Half-life. This one is given to you on your equation sheet. These other two, you don't need to memorize. Okay? There's nothing to memorize. All right? Let's look at a sample problem. Are you ready? Here we go. Okay. Much like I just erased off of the board. You have a data table to go with this equation times molarities. And it says determine the rate law. Well, that would be great, but I don't know what the exponent is supposed to be. So that's what we need to figure out. Here's the good news. You are not going to have to graph anything yourself. The graphs will be generated for you. Your job will be to interpret those graphs. Okay? So in your mind you say, well, let me see if it is zero order first, because that's the simplest one. And there would be a graph already drawn for you. What would be on the x-axis? Time? To test for zero order, what would be on the y?
Concentration.
Just plain old concentration. I'll just put a set of brackets. And let's say this graph that has already been created for you looks like this. Does that look straight to you? Doesn't look straight to me. What does that tell you? It's not zero order. Okay. So you say, well, maybe it's first order. Let's try that. And then there might be a second graph already drawn for you. To test for first order, what would be on the x? Time. What would be on the y? Natural log of concentration. And let's say that graph looks like this. Straight? Nope. What does that mean to you? It's not first order. Now, what's the only other option? It must be second, but usually you're going to see a third graph that would prove this to you. So let's just draw that out. Time would be on the x. What would be on the y? 1 over. Straight? Yes. So you say, okay, it's first, or excuse me, this graph is telling me this is second order data. Determine the rate law? Okay, fine. Here's what a second order rate law looks like. Rate equals. And I know that it is to the second power. First part of this problem done. Determine the rate law, check. That's all I have to write. Determine the integrated rate law. Nothing to memorize, it's here. The only thing you need to change is instead of writing the letter capital A in the brackets, put what the reactant actually is. Make sure, guys, if you are asked to write the integrated rate law, make sure you put that little sub-zero. If that sub-zero wasn't there, it would be marked wrong. You have to make sure there's a difference between the initial and the final. So, check off that second part. Final part, and this is the hardest part. And I'm going to give you some time to kind of wrestle with this. They want a value for K. They want an actual number. So here's what I'm challenging you to do. Look at what we have access to. We have two rate laws. We have a table of data. We have a graph, but the graph doesn't have any numbers on it. There's no scale on these axes, so I can't use this graph to get any numbers off of it, but I do know that that's a linear straight line. Take a few minutes, talk with people around you. See if you can figure out how are you going to find a value for K. Let's talk out this last part. Throw out some ideas. What do you got? What do you want to try? Plug in what? First of all, plug into what equation? Which one? Okay, the integrated. Okay, so what do I plug in? Okay, so pick a point. Pick 2 points. Right. I don't have a number I can plug in there because I wasn't given. Remember what this is. This is the molarity at time 0, which I don't have. I saw a couple of people plug in this value right here in this position just because it was the first data point, but that's not correct because this isn't at time 0. So we don't have that value. Other suggestions? Okay, he said something about slope. Okay, so this slope, is that what you're talking about? Okay. So slope, you pick 2 points, right? Let me erase. Does it matter which 2 points I pick? No. I'm just always in the habit because my algebra teacher beat it into us. You always pick the first and the last point. Fine. But you got to be careful with this. Okay? Slope, fine. Slope is change in y over change in x, right? Tell me why it would be incorrect for change in y, this number, minus this number. It's wrong. Why? Thank you. Yeah, what's on the graph here? It's not just molarity, it's 1 over. You have to be really careful. That's really sneaky. So change in y, okay, fine. 1 over. I'm going to take it out of scientific notation, so it just annoys me. Now change in x, I don't have to do anything fancy with that. Okay. Somebody give me a number. What do you get? 0.014? Okay, well, that's great, but how does that help me? Say it again. That is the K. Y equals M. Slope. The slope is K. We just solved the problem. That's our answer. Great question. What are the units? Okay. Wait. Remember, the trick is the little pattern. Tell me, guys, what is the overall reaction order? 2. Remember the trick I showed you last class? The trick is the units are m to the negative 1 number less times time, or you know what, let's be more specific since we know it's seconds. Inverse seconds. That is K. Right? So this problem, they gave us a data table, but guess what? Sometimes they won't. Sometimes they won't give you a data table at all, but instead will give you a graph that actually has numbers on each axis so that you could truly do rise over run, that whole deal. Okay. That is all, my children. I'm stopping there.